Okay guys, so in this video we're going to talk about trigonometric substitution. Now this is sometimes referred to as inverse trig substitution, but that's not to be confused with inverse trig functions like arcsine, arccosine, or i.e. like sine inverse sine to the -1. It's not to be confused with that when we say inverse trig substitution, we kind of just mean it in the sense of like the English sense of inverse, which is kind of like the reverse or whatever, the opposite. Um, so you will see why that's called that way in just a sec. I'll explain it more, but basically, in order to understand trig substitution, you have to understand trig integration because trig substitution is going to be taking functions of x, converting it into trigonomic functions of theta, in which case they will be of the form of our previous sections on trig integration, and we use trig integration methods to integrate it, which is often u sub. So what's the inverse is to say that basically instead of turning trig into like algebra equations to integrate, we convert algebra into trig, then we convert trig into algebra. So that's what we mean by this kind of inverse. And we'll see those in examples. Like we do that every time. All right, so let's first talk about the issue. Basically, when finding the area of a circle or ellipse, we have an integral of some basic form here. Integral square root a squared minus x squared. Now, this comes from the circle formula, y squared plus x squared equals 1 squared. In this case is the unit circle. The constant determines the radius. So this constant square root is the radius. So in this case, 1 squared square root is 1. It's the radius here. If we change this to 3 squared, i.e. 9, then the radius would be 3. If we change this to 3, the radius would be the square root of 3. So a few things to note is that when we're talking about this, it doesn't actually have to be this perfect form. It doesn't have to be a perfect square. It could be something we take the square root of. It also doesn't actually even need a square root, but you usually recognize it via the square root. Because, I mean, if you think about it, like, if we just wrote this in solve for y, but without, so solve for y squared equals 3 minus x squared. This thing here is still describing, you know, the curve that we have here. We don't need the square root, but this isn't a function. So we often describe it in terms of a function. So that's something to be aware of. It doesn't need to have that thing, but it is worth mentioning that. The problem here is that basically when it's in this circular form, we don't actually have a method to integrate this function. Like we know we should be able to. I mean, it's just it's a function. I mean, there's nothing special here. This is a function. Why shouldn't we be able to integrate this, right? So what we do is instead of thinking about this in terms of the points on the circle via a circle, what we instead do is we think about it in terms of a triangle. So we start marking each point along this circle in terms of some triangle, talking about it in terms of an angular measurement. So for example, here at 1/2, okay, or whatever, then let's just turn this into a, okay, we do have it. So for example, at like 1/2, x equals 1/2 or whatever, we instead describe it as like sine of an angle, or maybe cosine of an angle, or secant of an angle, or tangent of an angle. In reality, we use three different ones, but the point is that we start changing that, and so that's based around this unit circle concept. If you think back, you know, sine of 30 degrees or pi 6 is 1/2. So essentially, rather than talk about it in terms of our ordered pair through kind of following this circular line, we instead talk about it through angle measurements, sine of some angle or whatever. Okay. So you don't really have to get too worked up about that, but this is where it's derived from. I'm not going to derive it. Basically, we have a table of trigonometric substitutions that we use. So we have, if we have a form square root a squared, that is some constant, minus x squared, the one that we started with, the basic circle, okay? Then we use the substitution x equals a sine theta, where x is the value here, the variable that's being squared. A is our constant that's being squared, and then theta is our variable. So we're going to turn everything from x's into thetas using this substitution. Now, this is going to be true on the interval from negative pi halves to pi halves. That would be quadrant 1 and 4, i.e. the right hand of the circle. So it's true on this side, but you don't actually have to really think too much about it. It works itself out. So I don't ever really think about this interval because it's just a short step to get us to the next step, and it works itself out. The next one is if we have the square root of a squared plus x squared format, then we're going to use x equals a tangent theta. So in this case, it's on the same interval from quadrant 4 to quadrant 1. And again, same thing. A is our constant, x is our variable portion, and theta is our variable we're changing it into. Now, I mentioned before that a doesn't have to be a perfect square. So, like I said, if we had something like square root 3 plus x squared, then this would be x. So we'd use x equals a, which would be the square root of 3, tangent theta. Now, this also doesn't have to be a perfect x. If we had something like the square root of 9 plus, I don't know, 2x squared, something like this, then you could technically rewrite this as 2 square root 2x squared like this, and call this basically your x term. So you would say, in this case, you would say like square root 2x equals a, which would be 3 tangent theta. So it's not restricted to just x, though it usually just sees x. And it's not restricted to a perfect square, though we often see perfect squares, but not always. We often see it probably more as a construct of a math class than the real world. Okay, so the last one we use is when we have x squared minus a constant squared. So instead of our first one, which was a constant squared minus x squared, we use x squared minus a constant squared, and this is going to be x equals a secant theta. Now, it is only true between, essentially on quadrants 1 and 3. So that is to say, kind of here and here. Terrible circle, but you get the idea. These two quadrants. Again, don't have to worry about it. Essentially, we're going to use trig identities as well. A lot in here are Pythagorean identities. So that's what these identities here are mentioned. So anyway, so the point is that we will often use these these Pythagorean identities to then cancel out. So essentially, we turn it into this sine, then we have something minus sine squared, like 1 minus sine squared is cosine squared, so we then convert it into a cosine squared theta, and the square root and the squared cancel, and we get something nicer. So essentially the idea is to cancel out the square roots, but as mentioned, it's actually not restricted to just square roots, but we generally see them in square roots, because the square roots are often the problem. Okay, so let's go ahead and take a look at some examples. Okay, so we have x cubed over square root 1 minus x squared dx. Now, this one screams inverse trig substitution to me because we have square root 1 minus something squared, or 1 plus something squared, or something squared plus or minus something squared, and it's in a square root. That's screaming. Also, it's on the bottom. That's also, it doesn't have to be on the bottom, but that is so common that it's worth noting. Okay, so it's a 1 minus x squared. So if we go back here, as a reminder, that's going to be a sine. So we're going to say x is a, which in our case is 1, sine of theta. Okay, so that means that dx then, if we derive this, derivative of sine theta is going to be cosine theta d theta. Okay, so basically what we want to do here is we want to replace our x's with thetas and our dx's with d theta. Now, in traditional u substitution, we would find a cosine theta, or we'd find something to replace, like maybe like an x squared out of here and a dx to make the du, okay? But for us, we don't really have any way to do that, but that's okay because dx is equal to cosine theta d theta. So our x cubed x is sine theta, so that's going to be sine cubed theta. Our dx is going to be cosine theta d theta. And on the bottom, we have square root 1 minus x squared, x being sine squared, or x being sine, so this would be a sine squared theta. So we have replaced all of our x's into thetas. Now, a few things to note with this conversion here. We're basically using our right triangle. If we call this this thing here theta, sine of theta is opposite over hypotenuse. Okay, so sine of theta is opposite x over hypotenuse, just a 1. So this right here would be square root 1 minus x squared. Okay, based on the Pythagorean theorem. So this thing squared plus this thing squared is 1. Okay, squared. All right, so we're going to clean this up a little bit. The square root 1 minus, and we'll use this later. Okay, so the square root 1 minus sine squared, well, if we go to our trig identities, we have Pythagorean identities. So 1 minus sine squared is cosine squared. All right, so we're going to have the integral of sine cubed theta over square root cosine squared theta times cosine theta d theta. Alrighty, so square root and squareds cancel, cosine cancels, and we're left with the integral of sine cubed theta d theta. All right, so when we're integrating sine cubed theta d theta, we can now use some methods that we might have on hand. So for example, if we want to do a sine cubed, well, if we think about that, that's like saying sine squared theta times sine theta. So if I were to replace this thing with like Pythagorean identity, so again, going back here, sine squared is 1 minus cosine squared. So this would be 1 minus cosine squared theta times sine theta d theta. And if I were then to call cosine theta my u, then that means then that derivative of cosine is going to be negative sine theta d theta is equal to du. So I have a sine, I have a d theta, I just need a negative. So we'll put a negative in, pull a negative out. We have negative integral of 1 minus u squared du. Alrighty, so we can now integrate these individually. So the integral of 1 is going to be negative here u. Then a negative and a negative makes a positive, u cubed over 3 plus c. Now we are going to start replacing these u's back to where we started. We actually didn't start in thetas, we started in x's. We'll use these eventually. So let's first start by replacing our u's with thetas. Okay, so u is cosine theta. So we have negative cosine theta plus cosine cubed theta over 3 plus c. Okay, so I said that we're going to use this triangle. We're going to use it now. Well, we can also copy all of these if we want, because sometimes it's necessary to have the x as well. So I'm just going to copy it all. But generally speaking, it's often sufficient to just have our little triangle that we created through the Pythagorean theorem and SOHCAHTOA. So we have our little right triangle that, again, if theta is this angle here, then sine of theta is x over hypotenuse, x over 1. And then using Pythagorean theorem, we see that this thing here, I mentioned it, but let me just show it. If we have this thing squared plus x squared, this should be 1 squared. So let's see, those cancel. 1 minus x squared plus x squared equals 1. That's true. So this is Pythagorean theorem here. It's always, that other one's just going to be that one that you use for your substitution. That's honestly where that substitution comes from. So anyway, we have this thing. So what's cosine of theta? Well, sine of theta was x over 1, but cosine of theta is adjacent over hypotenuse. So this would be negative square root 1 minus x squared over 1, which I don't need to write, plus, again, cosine of theta is adjacent over hypotenuse, so square root 1 plus x squared to the third over 3 plus c. Now you could obviously write this like 1 plus x squared to the 3 halves if you want, but this is sufficient. So this is our integral. Okay, let's take a look at another one. Okay, so we have x cubed over the square root 9 plus x squared. And again, same thing, square root on the bottom, sum or difference of squares. This is inverse trig substitution for me. Now, in particular, this is our second one here. X is a tangent theta. So we're going to go ahead and use that. So again, we have the x is a tangent theta. So our a here, this would be like 3 squared. That's our a. So x is 3 tangent theta. Okay, so that means that dx then is going to be, the derivative of tangent is secant squared, so we have 3 secant squared theta d theta. All right, so our triangle, if this is theta, okay, basically we have, if we solve for tangent theta, we divide by 3, we have x over 3 is tangent theta. Now, tangent is opposite over adjacent, so that is x over 3. And this then would be 3 squared plus x squared is c squared, square root of 3 squared plus x squared. That's this thing here, square root 9 plus x squared. Okay, so we're going to use this again later when we come back into our substitutions. Alrighty, so if we take a look at this thing, we go, alright, so let's start replacing these things. So x is 3 tangent theta. So that is to say x here is going to be our 3 tangent theta cubed over, so this thing here, the square root of 3 squared, I'm going to go ahead and write it like that, plus x squared, which our x is 3 tangent theta, which would be 3 squared tangent squared theta. Okay. Dx we're going to replace with 3 secant squared theta d theta. And this is all our integral. Okay, so now when we take a look at this thing, we're going to clean this up a little bit. 3 cubed, I'm just going to write it as 3 cubed to save my life in case this gets worse. So we have 3 cubed tangent cubed theta over square root. Now, 3 squared is in both of these. I'm going to factor that out. If I pull out a 3 squared, I have 1 plus tangent squared theta. And here we have a 3. So really, I'm going to go ahead and put this 3 with this 3. So it's a 3 to the 4th now. Secant squared theta d theta. Okay, so now we're still integrating this thing. I'm going to pull this thing here, the square root of 3 squared. Now, as a reminder, if we have a product of two things, a and b, in a square root, this is like saying the square root of a times the square root of b. So I can do this. I can take the square root of 3 squared and pull it out. So the square root of 3 squared is just 3. So essentially, we have 3 to the 4th over 3, which is just going to be 3 cubed. And I'm going to bring it out. So we have tangent cubed theta over the square root of 1 plus tangent squared theta. Now, 1 plus tangent squared theta is secant squared theta. I'm going to replace that. Okay, so square root and squared cancels. And we have a secant, which will cancel with one of those secants. And we end up with 3 cubed times the integral of tangent cubed theta secant theta d theta. Alrighty, now we need to integrate this thing. So this is just our basic trig integration now from 7.2. So if we want to integrate these things, again, same thing as before, we want to keep in mind that we basically have a tangent squared and a tangent secant, or we would have a, well, that's pretty much what we need to think about because we don't have a secant squared. So we don't want our u to be tangent, because the derivative of tangent is secant squared, but the derivative of secant is secant tangent. So I'm probably going to choose u to be secant theta. That means then that du is secant theta tangent theta. So if we think about this thing here, we have a secant, we have a tangent for our du. I should write a d theta here. So we have 3 cubed times the integral of tangent squared, tangent secant d theta. So that's going to give us du. Okay, now we want to replace this tangent squared as a reminder. Tangent squared is secant squared minus 1. So 3 cubed integral. Again, tangent is secant minus 1. So we have secant squared theta minus 1. Okay, du. Now, secant is our u, so we have 3 cubed integral u squared minus 1 du. And now we can integrate this thing pretty easily. We have 3 cubed times u to the third over 3 minus 3 cubed u plus c. All right, now we're going to start replacing everything back the way they should be. So I'll start by replacing this as a 3 squared. U to the third, instead of u as a reminder was secant. So we have secant cubed theta minus 3 cubed secant theta plus c. Now we're going to use our triangle that we created and potentially our substitution, but for now I think we'll be fine. We don't just have like x's on their own or anything like that, or thetas on their own. So secant, as a reminder, secant is 1 over cosine theta, okay? Now cosine, so that's 1 over, our cosine is adjacent over hypotenuse, so that is hypotenuse over adjacent. That's what that is. So hypotenuse over adjacent. Okay, so we have 3 squared times hypotenuse, square root 9 plus x squared over adjacent 3. And this is all being cubed. Minus 3 cubed times secant, again, is square root 9 plus x squared over 3 plus c. Okay, so this would be a 3 cubed and a 3 squared. Would make this just a 3 to the 1. So we have square root 9 plus x squared cubed over 3. The 3 and this cubed will cancel to make squared, so that's going to be minus 3 squared, square root 9 plus x squared plus c. And yeah, I could write that as a 9 at this stage if I wanted. Maybe that would look better. Doesn't really matter. So now we are in terms of x's, which is where we started. So again, that would be our integral. All right, let's take a look at another one. Okay, so this is a definite integral from 2 to 3. On top, we don't really have anything. It's just dx. We could just write it out in front as well. We have an x squared minus 1. Now, if we go back to this thing, this is our only x squared minus something. If it was like x squared plus something, we'd just reorder it, no big deal. But here, these are different things, so we need to make note of it. So we're going to use our x equals a secant theta. Okay, so let's go ahead and take a look at this thing. We have the integral 2 to 3. We have 1 over. Now, this is hidden, but it's still a square root. It's like saying the square root of x squared minus 1 cubed dx. So this is what we're working with. So again, we're going to use our square root. X squared minus a squared is our x is a secant theta. So we have x equals a secant theta. So for us, our a is 1. Our x is just x here, so x equals secant theta. So that tells us then that dx is going to be the derivative of secant is secant tangent. Secant theta tangent theta d theta. And our triangle, if this is theta, again, secant, as a reminder, is 1 over cosine. And again, that's 1 over our adjacent over hypotenuse. So that is, it would be hypotenuse over adjacent. Okay, so hypotenuse, x, over adjacent, 1. This right here would be square root x squared minus 1. Again, it's just this square root. So, but we can use Pythagorean theorem to show that. This thing squared plus this is x. So squaring this would be x squared minus 1 plus 1 would just leave x squared, would be x squared. Okay. So we're good here. Let's go ahead and start replacing these things then. So x is secant squared, or secant theta, so we're going to end up with the integral from 2 to 3. Now, something to note as well is that these bounds of integration are in terms of x. So when we change this into theta, they're not going to be true anymore. We could change them into theta, and in problems like this, sometimes I do it, sometimes I don't. It kind of can save us work to change these along the way. Otherwise, you have to change them all back to x's before using our definite integrals. So we could actually change these boundaries while we're at it. So if x is secant theta, then our x here is 2. So when 2 is secant theta, then what would theta be at that stage? Well, secant inverse of 2. So this would be secant inverse 2 if we want it to be. Same thing, if we have 3 as secant theta, then we'd have secant inverse to get theta. So this would be a secant inverse 3 if we're changing these into thetas. So you can do it. It depends. It just really depends on the problem. Sometimes I do it, sometimes I don't. Sometimes it's not worth it. I often save it until the end to determine whether it's worth it, though. So I don't necessarily do it right away, but if it helps, definitely do it, because you don't want to get everything to the end and then use the wrong bounds of integration. That would be a problem. Okay, so we have 1 over the square root. So square root secant squared theta minus 1. Dx is going to be our secant tangent d theta. So secant theta tangent theta d theta. And this is all cubed. Okay. So if we have this thing, we have this bound of integration still. I'm not going to write them every time at this stage because that's a nasty thing to write, and that's why I often just save it to the end. So we have 1 over. Now, the secant squared theta minus 1 would be tangent squared. So we'd have the square root of tangent squared theta cubed times secant theta tangent theta d theta. So that means then that these would cancel and I'd have a tangent cubed. Okay, so we have the integral of secant theta tangent theta d theta over tangent cubed theta. Alrighty. Cancel this, and we end up with the integral of secant theta over tangent squared theta d theta. Okay, so with something like this, we have some options available to us. When I have sines and cosines, tangents, whatever, on top of each other, I think about them in terms potentially of like fractions. So as a reminder, secant is like saying 1 over cosine. So this would be like 1 over cosine theta over tangent is sine over cosine. And these would both be squared here. So we could potentially use that. So that is to say it would be 1 over cosine theta times cosine squared theta over sine squared theta. And this would enable us to cancel. We end up with cosine theta over sine squared theta. This isn't to say that it's necessarily going to save us much work or anything. This isn't maybe any better, seemingly, than this one, but I just want to point out that that's something that's going through my head when I see something like this. Okay, so that's one option we have to us, but at the end of the day, basically what we have here is we have some substitutions. And one of the benefits to this is the derivative of tangent, which I would like to use as my u. Derivative of tangent is secant squared. We don't have a secant squared. Derivative of secant is secant tangent. We don't have a secant tangent. So that's why I'm not going to use this. Instead, I could potentially use this one. So in this case, if I'm integrating cosine theta over sine squared theta d theta, then I can do what I want, which is use this bottom one as my u. So if I call sine theta my u, then that means that cosine theta d theta is my du. I have a cosine, I have a d theta. So we have the integral then of cosine d theta is just going to be du. It's 1 over u squared. So this is what I'm going to be integrating. Now, something to note. When I change my thetas into u's, I have to change my bounds of integration into those u's as well. Now, I can use the same thing. So sine of theta is u. So I could take sine of secant inverse 2. But that's going to get really ugly. And so this is why I said that sometimes I wait until the end. I mean, we could certainly write that. So that is to say, I could have sine of secant inverse 2 and sine of secant inverse 3 if I want. But that's hideous. And I probably don't want to do that because it's probably not going to make my life better. It's going to make it a lot worse. Because usually we want exact answers. If we were just approximating, it doesn't really matter. But this is probably out for me then at this stage. So this is what I'm talking about, where it just depends on the problem, but these are definitely like good candidates for me to change my bounds of integration along the way. Anyway, so we're now in terms of u. Okay, so we need to integrate this thing. This is the integral of u to the negative 2 du. So that would be u to the negative 1 over negative 1 plus c. So that means that we end up with our u is sine. So we have negative 1 over sine theta plus c. Now, if you think about that, what's 1 over sine? Well, we could call that secant if we, or cosecant if we want. That's okay. It doesn't really matter. I would actually leave it as sine. I find it less confusing for me, and then deal with the fractions. But you could call it like your cosecant if you'd like. But we don't actually care about sine of theta. We don't care about thetas. We care about x's. So this is when we go back to our little triangle here that we created. So it just takes a little bit more mental gymnastics for me to do SOHCAHTOA in the cosecant, cotangent, and secants. So that's why I'm just leaving it as sine. Okay, so we have sine is opposite over hypotenuse. So that is negative 1 over opposite square root x squared minus 1 over x plus c. So that means that we have negative x over square root x squared minus 1 plus c. But we're doing a definite integral, and I've completed this back to x's, so I'm going to use my original x's from 2 to 3. If I wanted to leave it in u's, I actually could have just done this in those, but like I said, these are really hideous to me, so I don't want to use those. So instead, I'm going to do this from 2 to 3. Now this c is obviously not important in definite integral, but I do it just out of practice to make sure I don't make a mistake when I'm doing indefinite. All right, so we're plugging 3 in. We have negative 3 over the square root of 9 minus 1 plus c minus 2 would be negative 2 over the square root of 4 minus 1 plus c. So the c's, of course, cancel, and I really don't need to write them, but I like to show them anyway. We have negative 3 over square root 8 plus 2 over square root 3. This would be our definite integral. Okay, let's try another one. Okay, before we actually start with that, let me actually go back over this and mention something here. We can check this pretty easily with Desmos. So if we take a look at this thing, and we go to our keyboard here and go to functions, if we go down to our calc, we can take the integral from 2 to 3. Since it's a definite integral, we can do this and double check that what we got agrees. So it's not going to be exact as far as, like, if you do the definite integral here, it's going to give you a decimal approximation, but to test whether or not we're correct, it's going to work just fine. So we have this thing here to the 3/2 dx. Okay, we get that value. Now let's test that against our value we just got, which is going to be -3 over the square root of 8 plus 2 over the square root of 3, which is the same value. So that's good. All right, let's go ahead and take a look at our next one. We have the integral x cubed over square root 1 plus x squared dx. Okay, so this one's pretty similar to our first one. The only difference is now we have a plus. So our plus one is going to be a tangent theta. So we're going to use x is a tangent theta. So for us, we have our x is a 1 tangent theta. So that tells us our triangle, terrible triangle, but whatever, theta. Tangent is opposite over adjacent x over 1, so this would be the square root 1 plus x squared. Okay, so dx is going to be secant squared theta d theta. All right, let's go ahead and start replacing these things. We have the integral. X cubed is going to be tangent cubed theta over square root 1 plus x squared. Our 1 plus x squared, that's going to give us 1 plus tangent squared theta. And our dx is going to be secant squared theta d theta. Okay, now 1 plus tangent is secant squared. So we have the integral of tangent cubed theta over the square root of secant squared theta, secant squared theta d theta. These would cancel, and one of these would cancel with one of those, and we end up with the integral of tangent cubed theta secant theta d theta. Okay, now we have a tangent secant, so that tells me I'm going to have to use a secant. We don't have a secant squared. Okay, so we have our tangent squared theta times tangent theta secant theta d theta. That's what this integral actually is. So we're going to say u is secant theta. Du then would be tangent theta secant theta d theta. We have that. And we're going to replace our tangent squared again. Tangent squared is secant minus 1. So we have the integral of secant squared theta minus 1. That's our tangent squared. Our tangent secant d theta is du. And I should have not done theta in a sec. Well, it is theta, but we'll now replace it with u's. So secant theta is in u. So that's u squared minus 1 du. So the integral of u squared is going to be u cubed over 3 minus u plus c. All right, now we need to start replacing our u's with secant. So u is secant theta. So we have secant cubed theta over 3 minus secant theta plus c. But again, we don't care about thetas either. We care about x's. So we're going to go ahead and use our little triangle here. Okay. So secant, again, is 1 over cosine. So that is to say it is our hypotenuse over adjacent. Again, I have to do a little bit of mental gymnastics, I feel like, when I do stuff like that. So I often do like 1 over adjacent over hypotenuse. I just find that easier, but whatever. So it's hypotenuse over adjacent. So that is to say it's the square root 1 plus x squared cubed over 3 minus square root 1 plus x squared. So it's over 1, but then it's over 3 here. So I didn't write the over 1. Over 1 plus c. And now we're back in x's. So that is our integral. All right, let's take a look at another one. Okay, so we have a square root now on this one. So it's x cubed square root 16 plus x squared dx. And this is our integral here. Now, if we're looking at this thing, we could maybe try something like, if I'm looking at something like this, maybe 16 plus x squared is our u. Now, in general, we use our inverse trig substitutions when our square roots are on the bottom, but that isn't to say we can't use it when it's on top as well, but sometimes there's better options available. So if we have this thing as our u, we would have 2x dx is our du. Okay, so we can replace this. So this is the integral of, so one of our x's, so we're going to put a 2 in and pull a 1/2 out. So we have 1/2 times the integral. So 2x dx becomes our du. We have an x squared left behind, and then we have the square root of u. Okay, now we still have an x squared left behind, but let's go ahead and move this 16 over, and we get x squared in our u substitution equation. U squared is going to be equal to u minus 16. So I could write this as 1/2 integral of u minus 16 times u to the 1/2, which is the square root of u du. And then I can distribute this thing. So distributing this in, we have 1/2 integral u to the 1 times u to the 1/2 is going to be 3/2, u to the 3/2 minus 16 u to the 1/2 du. And then we could integrate this thing pretty straightforward. So we would end up with 1/2 u to the 5/2 over 5/2 minus 1/2 times 16 is going to be 8 u to the 3/2 over 3/2 plus c. So notice we can actually do this without any kind of like inverse trig substitution, because this power is on top and it's actually making that integration much easier to be done with some u substitution. That isn't to say that we can't do that in other problems necessarily, but yeah, if I see it that I can do basic u sub, then why not just do that? That sounds a lot easier. But either way, we'll take a look at both ways. So 1/2 times 5/2, or times divided by 5/2 is like saying times 2/5. So we have 1/2 times 2/5. Instead of u, as a reminder, u was our 16 plus x squared. 16 plus x squared to the 5/2 minus, so this is 8 times 2/3. 16 plus x squared to the 3/2 plus c. So that is to say our problem here will be 16 plus x squared to the 5/2 over 5 minus 16 over 3 times 16 plus x squared to the 3/2 plus c. This is our solution using u substitution. But let's go ahead and try this same thing with integration using our inverse trig substitution. Because there's not necessarily like a right or wrong way to do problems sometimes. It's just a matter of what you see. Okay, so we have this square, or the integral of our x cubed here. So we have a 16 plus x squared. So that's going to be a sum here, a tangent theta. So x is a tangent theta. So for us, that means that our x is going to be 4 because 4 squared is 16. So 4 tangent theta. So that means that x over 4 is our tangent theta, and that's going to help me with my triangle. So let me go ahead and draw that. So tangent is opposite over adjacent. That means the hypotenuse is 16, square root 16 plus x squared. Okay, so we have our little triangle drawn. Now let's go ahead and find the derivative of this thing. So dx is equal to 4 secant squared theta d theta. Okay, so now we're going to start replacing these things. Integral x cubed. Our x cubed is going to be 4 cubed tangent cubed. So 4 cubed tangent cubed theta times the square root of 4 squared here. I said 4 cubed. I hope I said 4 cubed. 4 cubed tangent cubed theta. Square root, this is now 4 squared, plus our x is going to be, x squared here is 4 squared tangent squared theta. And I'm going to replace my dx with our 4 secant squared theta d theta. All right, now we'll do some cleanup work here. So 4 cubed and 4 makes 4 to the 4th outside, 4 to the 4th outside our integral. We have tangent cubed theta times the square root. Now in here we can pull a 4 squared out. What's left behind is 1 plus tangent squared theta. And this 4 squared can be pulled out in front of the square root as kind of like a 4. So really I can just put it as a 4 to the 5th. Okay, we still have our secant squared theta d theta. Okay, so we end up with tangent cubed theta square root. Now 1 plus tangent squared, as a reminder, going back here, 1 plus tangent squared is secant squared. So we have secant squared theta times secant squared theta d theta. Now the square root of secant squared is just secant. So we have 4 to the 5th integral tangent cubed theta secant cubed theta d theta. Okay, so now in this problem we have both a tangent secant and we technically have a secant squared, but again, because I have a tangent secant here, I'm probably going to use secant as my u substitution, because if I chose like tangent is my u, I have a secant cubed, and that's not good. That's not an even power. If it's a secant squared only, then that would be fine. So again, I'm going to go with probably my u is secant theta. So that would mean that du is going to be secant theta tangent theta. So that means that we can kind of start pulling these out. This is 4 to the 5th times the integral. So we have a tangent squared theta left behind. We're reserving one tangent, a tangent and a secant. So we then have a secant squared left behind as well. The secant and the tangent that we pulled out of those cubes is going towards our du. And we also have a d theta, so that's good. So we end up with just du. So we have tangent squared theta, secant squared theta, du. Now we're going to start replacing these things. Secant can just become u, but tangent squared, as a reminder, tangent squared is secant squared minus 1. So we have 4 to the 5th integral secant squared theta minus 1 times secant squared theta, which we're going to call u squared du. And we can now replace our secant squared with a u squared as well. So we have 4 to the 5th integral u squared minus 1 times u squared du. Okay, so we can now distribute our u squared into our u squared minus 1, and we get 4 to the 5th times the integral u to the 4th minus u squared du. And we are going to integrate this thing. So we have 4 to the 5th u to the 5th over 5 minus 4 to the 5th u to the 3rd over 3 plus c. Okay, so now we can start replacing these things. So u to the fifth was, so u is secant, so we end up with 4 to the fifth over 5 secant to the fifth theta minus 4 to the fifth over 3 secant cubed theta plus c. Okay, so we're now in thetas. Let's go ahead and convert those thetas back into x's using our little triangle here. Okay, so as a reminder, secant is 1 over cosine, so that is hypotenuse over adjacent. So hypotenuse over adjacent is going to be 4 to the fifth over 5 times hypotenuse over adjacent. So again, that is square root 16 plus x squared over 4 all to the fifth minus 4 to the fifth over 3 square root 16 plus x squared over 4 to the third plus c. All right, so this 4 to the fifth and this 4 to the fifth will cancel, and so it's just the fifth on the top, because this fifth goes to the top and the bottom. So we end up with the square root of 16 plus x squared to the fifth over 5 minus, so in this case, a 4 to the third, and this becomes just a 4 squared or 16, so it's minus 16 over 3 square root 16 plus x squared to the third plus c. So we have our integral. Now, it doesn't really matter which method we choose. If we take a look back over here, we have the same thing. 5 halves, 3 halves, 5 halves, 3 halves. They're the same thing. It doesn't matter which method we use. Obviously, u substitution was easier, and so if you recognize that you can do something easier, then do it. But a lot of times, we're stuck using our inverse trig substitution, not because we want to do it, but because it's the only way we can think to do it, or whatever. U sub just wouldn't work. But as mentioned, U sub would totally work on that one. All right, let's take a look at another one. So we have the integral square root 2 minus x squared all over x squared dx. Okay, so again, in this case, our square root is on top. That's not super normal, but it's common enough that we shouldn't be thrown by it. This is still, I'm seeing a square root. Now, I'm not seeing a perfect square, which is also something that maybe raises some red flags, but anything could be made to be a perfect square if you think about it. I mean, it's not, quote, perfect, but anything could be written as a square, I guess. So that's not really a bad thing either. So this is kind of breaking two rules for us, but that doesn't mean that we're not going to use our inverse trig substitution. Basically, the issue here is that we don't have, like, if we chose the inside to be a u, 2 minus x squared is u, then we'd have a negative 2x dx as our du. We don't have a negative 2x. We have an x squared on the bottom. So that's problematic for us. If this was reversed and like the x squared was on top, then that's maybe something we could work with. But as is, it isn't something we can work with. So we are left going to integration by inverse trig substitution. So let's first talk about this one. The top here, this 2 minus x squared, that's like saying the square root of 2 squared minus x squared, if you think about it, right? Because the square root of 2 squared would be 2. So we can write it like that. So in that form, we go back here. We have a squared minus x squared. That's a sine here, a sine theta. So we're going to use x is a sine theta here. In this case, our a is square root 2. So we have x equals the square root of 2 sine of theta. So for our triangle, I'm going to solve for sine theta real fast. That means that x over square root 2 is our sine theta. So that's going to help me draw my triangle. Let me draw it real fast, theta. So sine is opposite over a hypotenuse. So that would be x over x and our square root 2 here as our hypotenuse. So that would mean then that on the bottom we have square root 2 minus x squared, the adjacent angle, or the adjacent side, excuse me. Okay, so let's go back to our x is square root 2 sine theta. That means that dx would be square root 2. The derivative of sine is cosine theta d theta. All right, now let's start replacing everything. We have the integral square root 2 minus x squared. Our x is square root 2 sine theta. So square root 2 squared would be 2 sine squared theta over x squared. Again, that's just going to be 2 sine squared theta. Our dx we're going to rewrite as square root 2 cosine theta d theta. All right. So this is pretty ugly. I apologize for the writing there. Okay. On top, I can factor out a 2. If we pull out a 2, that leaves behind 1 minus sine squared theta over 2 sine squared theta square root 2 cosine theta d theta. Now we'll clean this up a little bit more in just a sec, but first I'm going to pull out this square root 2 as just a square root 2. I mean, we can do that. It's not a perfect square, but that's okay. Square root 2 times the square root of 1 minus sine squared theta times square root 2 cosine theta d theta all over 2 sine squared theta. Okay, so square root 2 makes 2, and the 2 on top and the 2 on bottom then would cancel, so all of those are gone. 1 minus sine squared theta, so 1 minus sine squared is cosine squared as a reminder, so we have the integral square root cosine squared theta times cosine theta d theta all over sine squared theta. Okay, so we would end up with a, so the square root cosine squared makes just cosine times cosine. We have the integral of cosine squared theta over sine squared theta d theta. Now, this cosine over sine, as a reminder, sine over cosine is tangent, so cosine over sine is cotangent. So we could write this as cotangent squared if only we had an elementary integral to that, but we don't. We have cosecant squareds and we have secant squareds, but for whatever reason we don't have cotangent squared as an elementary integral. So that kind of sucks, but that's all right. Let's try and think about what we want to do here. So if we have our cosine squared and our sine squared, we could certainly write one or the other in terms of the other, like if that's what we wanted to do. But that's not necessarily going to help us out here, because we would have like a 1 minus cosine or whatever if we would replace the sine. And as far as squareds, I mean 1 minus cosine squared instead of sine squared. And so that wouldn't necessarily make our lives any better. Let's try it though with the top. So if we replace cosine squared, so cosine squared is 1 minus sine squared. So I have 1 minus sine squared theta over sine squared theta d theta. Now this might be something I can work with, because I can split the top at the minus here. So this is like saying the integral of 1 over sine squared theta minus sine squared theta over sine squared theta d theta. Now this is pretty easy for me here, because we have the integral. Now 1 over sine squared would be like cosecant squared theta minus 1 d theta. So I can integrate this thing, and if we go to our elementary integrals table, let me pull that up here. Okay, we actually have one for this. So if we look, cosecant squared du is the integral of cosecant squared u du is negative cotangent u. So that we do have. So we end up with the integral of this is negative cotangent theta and minus theta plus c. So we have a negative cotangent theta minus theta plus c. Okay, so this is one of those situations where we just have a theta, and in this case, the triangle won't be sufficient for us. We also will need our x equals square root sign thing to make our lives better. But we'll take a look at that in just a sec. Okay, so here is our little triangle, and I'm going to go ahead and pull these things as well. Don't really need the blue one, but it got dragged into it. So let me paste these here as well. So like I said, don't need this. Okay, so I could use either any of these things. I actually don't need this one either, the dx. So I just need one of these for our x's here. Basically, I need to solve for theta here, because as is, we don't have anything for theta. We have things that we can use our triangle for, like cotangents and stuff. But anyway, so as a reminder, cotangent is 1 over tangent, which is, tangent is opposite over adjacent, so cotangent is adjacent over opposite. So we have negative square root 2 minus x squared over x. That is our cotangent theta in terms of x. Minus, now theta. Well, how do we find theta? Well, we can look at our x equals statement. So x over square root 2 is sine theta. So how do you solve for theta? You sine inverse everything. So that is to say theta is sine inverse of x over square root 2. I really try not to do stuff like this as much as possible, having like sine inverses and stuff, because having like sines of cosines of secant inverses and things are pretty ugly. So I usually don't do this unless I have to, but when we just have a theta, we're stuck doing that. So we have minus sine inverse of x over square root 2 plus c. And that is going to be our integral. So that has been our trigonometric substitution. So again, sometimes referred to as inverse trig substitution. Now, as mentioned, if there are easier methods, we like to use those, but a lot of times there isn't an easier method. Or maybe you just don't see an easier method, in which case we're stuck using those inverse trig substitutions. And a lot of times we can recognize them via square roots on the bottom of something plus or minus something else that are squared, so an x squared plus or minus something else or whatever. But like I said in this previous one, this last one here, you know, it broke all the rules. The square root's on top, which usually when I have a square root on top, I'm often thinking, oh, maybe just u sub. But square root was on top. Also, it wasn't a perfect square inside that root, but that's okay. We can work around it. Anyway, so that has been our trigonometric substitutions. Thanks for watching.